In this clip, we're going to discuss one particular feature of the information, which is once its aggregation is revealed to the public, it becomes a public good. And as all public good, you would have a free riding problem. So here we are going to present a simple math model that will prove that when in a group discussion settings, we do indeed have a free riding problem. So the setup is like this. We have a committee that has 3 people, and they are going to vote on the state of the world. If everybody at the beginning is agnostic about what it actually is, so it's no better than a guess, which that means the probability that you are right is about 50%. So one thing they could do is they could choose to pay cost 0.01 to become informed and make an educated guess that will raise the probability of being right to 70%. And if you are not informed, then you do not vote. And if the vote is tie, then we're going to randomly choose the correct state, 50-50. The important feature here that will make the information a public good is that once the result is out, everybody in the group gets to know. If it's right, everybody may enjoy the benefit. If it's wrong, everybody shares cost. So that means if someone else willing to invest and gets informed, I can actually sit there and reap the benefit of their hard work. So that is essentially why we have information as a public good here. So now let's think about a few situations. Now let's first think about what would happen if nobody is informed. So when no one is informed, you actually consider your option. You can either pay the cost 0.01 to get informed, or you can just sit there and do nothing. If you sit there and do nothing, nobody informed, nobody votes, so it's basically a weird tie. So we will going to randomly choose the state of 50-50. So the payoff is going to be 0.05. But if you get informed, the probability that you get it right, because you are the only people who vote, so your vote is the only vote that count, and the probability that you voted right is 0.07, minus the cost is 0.01, so you get a net benefit of 0.06. So it's actually optimal for you to get informed. So therefore, 0 people get informed is not equilibrium. So now let's consider the situation where 3 people actually get informed. So in this case, if already 2 people get informed, you're not getting informed, so there only be 2 people voting. If they both vote the right way, you will get it right. If they vote differently, so especially this be a special case of tie, there's 2 possibilities that they will get a tie. So because you can have A vote yes, B vote no, or B vote yes, A vote no. When they become a tie, you break the tie 50-50. That means 50 of the chance you will get it right. So at the end of the day, you get 0.07. Now consider the situation where you also get informed. So if all of you voted right, then you will obviously get it right. There will never be a tie because you have an odd number people. If 2 of you actually vote right, you get it right. And there's 3 cases that will happen. It's basically 3C, 3-2. And you need to pay a cost of 0.01. So you end up being with 0.684, which means if you know that 2 people will get informed, you will not get informed. So to all of you get informed will not be an equilibrium as well. So we know that if nobody get informed is not equilibrium, and not everyone get informed is not equilibrium, so the equilibrium must be somewhere else, somewhere in between. So now let's consider the situation where 1 people get informed. So when you expect at least 1 person will already show that they're going to get informed, if you do nothing, you get 0.07 because the informed guy will be the only guy who votes, and his vote will count. Now, if you also try to get informed, then you get back to the two-person vote scenario. The only difference is now that you have to pay the cost of 0.01. That is the learning cost. So now you actually end up getting only 0.06. So if you know someone will get informed, then you will not get informed. So that basically means that at the equilibrium, that will be only one people get informed, because if everybody does not get, and if nobody is getting informed, you will get informed. As long as one people get informed, you have no incentive to get informed further. So this is a classical example of free riding. It's basically someone's costly learning effort to provide extra utility to other member of the group. And this is actually a simplified version of a more general result, which says if you have a group N, if your group size is N, the committee size will be K. The committee is the people who actually get informed. So let's put a qualified word, informed committee. Is actually says K, and we know that K will be strictly smaller than N, but it will be strictly larger than 0. So someone will get informed, but not everyone will get informed. So this becomes a public good problem in the sense that the optimal amount for the group is maybe for everyone to get informed, because that gives you the biggest chance of getting it right. But since information is the public good, there is an insufficient supply of the public good. So how do we deal with the problem? One way to deal with the problem is that we will increase the transparency of the decision-making system. We'll expose people who do not vote. Okay, if you can expose people who do not vote, then you put some external pressure on their learning to learn the state of the world. So that is maybe one of the benefit of putting a C-SPAN into the Congress deliberation and voting, is at least they can't shirk from actually doing their job. Or I should say, if you don't have a camera in there, they might do an even worse job. But transparency is not always good. So in this case, we see that transparency works. In a different example, which will be the repetition model, we will see that increasing transparency will actually hurt good, honest behavior. So